There are three main categories to be covered. Descriptive statistics uses data to describe a population. Probability predicts the likelihood of an event happening. And inferential statistics uses data from a sample to make inferences about a population. A statistic is a numerical measure calculated from sample data, and a sample is a very small subset of a population. Data is normally organized in a table with m rows, which are the observations or data points, and n columns consisting of the variables. The variables can be anything from height, blood type, income, etc. There are two main types of variables, numerical variables and categorical variables. They're exactly what they sound like, number-based and category-based, respectively. Within numerical variables are continuous variables like height, these go along a wide continuous spectrum, and discrete variables like the number of doctor visits, these are often integer values. Variables can have different levels, which are the set of values that the variable can take. For example, blood type can be A, B, AB, or O. Variables can be positively associated when one increases, the other increases, negatively associated when one increases, the other decreases, or not associated at all, which is also known as independent. A key idea is that association does not equal causation, because there's often a confounding variable involved. This can affect both x and y. For example, height seems to cause greater math ability, but a person's age affects both height and math ability. So height and math ability are positively associated, but height is not causal for greater math ability. There are various types of data collection. Retrospective observational studies, which use past data such as medical record to look for patterns. And there's prospective observational studies, which collect data as it happens, similar to how data is collected during this pandemic. An experiment, on the other hand, is a controlled procedure which seeks to uncover if there is causation. There are 5 main components of experiments: a control and experimental group, randomization, blocking, replication, and blindness. We use various tools to compare data. For numerical data, box plots and histograms. For categorical data, tables. When comparing numerical and numerical data, scatter plots, and so on and so forth. A population is a set of values where n equals population size. The population has many parameters. The median is the middle value. The mean is the average of all the values. The variance is how spread out data points are from the mean. And the standard deviation is the square root of the variance. We often use standard deviation because it's in the same units as the data unlike variance. Here are the formulas for each, where the Greek symbol sigma stands for sum. Since we typically cannot reach the whole population, we cannot directly compute the population parameters, but we can estimate them using the parameters of a sample of the population. Here are the formulas for each sample parameter. There's also a note on how to find them using your calculator. A histogram divides data into bins or ranges, and the height of each bin shows how many data points are in each bin. Being the middle value, the median splits a histogram 50-50. The modality of the histogram is how many humps it has. It could be unimodal, bimodal, or multimodal. A box plot shows data in terms of the median and quartiles, Q1 and Q3, which create the box. The difference of Q3, the 75th percentile of the data, and Q1, the 25th percentile, is the IQR of the box plot. The whiskers are Q1 minus 1.5 times the IQR, and Q3 plus 1.5 times IQR. If there's no data point at that value, shrink the whiskers to the nearest data point. Here are some helpful visualizations. S is a sample space, or all the possible things that can happen. An outcome is something that can happen, also known as an element of S. An event is a set of things that can happen, also known as a subset of S. A union, symbolized as a U, of events means that one event, the other, or both happen. The intersection of events, symbolized as an upside-down U, is where both occur at the same time. Mutually exclusive means that when one event happens, the other cannot, while independent means that the events are completely unrelated, having no bearing on each other. P of A is the probability of A happening, which is equal to the number of events in A divided by the total number of events in the sample space. A union B and B union A are the same thing, as are the intersection of A and B and the intersection of B and A. In other words, order doesn't matter. Here are some rules to know, including De Morgan's laws, and please note that AC means A naught. In other words, where A does not occur. This is the same for B, C, etc. There are many axioms or self-evident concepts and propositions or statements of probability. Some things to note when familiarizing yourself with these axioms and propositions are that an underlined C means is a subset of, the weird E means belongs to, and pairwise mutually exclusive basically means that only one event can happen at a time. Here are some of the most critical formulas to know, the total probability theorem and Bayes' theorem being particularly common. Permutations are ordered arrangements, while combinations are unordered arrangements. Also be familiar with these formulas for the sum of n consecutive integers, the probability of k successes out of n trials, and the binomial theorem. It's important to note that the binomial theorem, it's called that because there are only two outcomes. Also, as a fun fact, Gauss created his formula when he was only in elementary school. The notation for the probability distribution of a random variable, RV, with the range from 0 to n and k equals 0 to n is as follows. Note that a random variable is a variable that can take any value within the range of values. The notation for a binomial distribution is as follows. There are also other distributions such as geometric and uniform distributions, but the binomial distribution is our primary focus. The expectation value, basically a weighted mean of a random variable, is found with this formula. Some rules to know are that for any two random variables, the expectation of the two added together is just the sum of their expectations. The expectation of a random variable multiplied by a constant c is just c times the expectation of the random variable. And the expectation plus c is simply the expectation of the random variable plus c. If x is distributed binomial np, then e of x equals np, var of x equals np times 1 minus p, and st of x equals the square root of np times 1 minus p. Note that a Bernoulli random variable is simply one trial of a binomial with a range of 0 to 1, probability y equals 0, or a failure equals 1 minus p, and probability of y equals 1, or a success equals p. For a random variable, mu of x equals e of x, which equals the following formula. Var of x can be found using m of x and mu of x squared, where m of x is called the second moment of x. Below are some rules involving variance, similar to the expectation rules on the previous slide, but using A instead of C. Gaussian normal random variables are normally distributed mu sigma squared. A normal distribution, symbolized with an n, means that the data is distributed along a bell-shaped curve, like how grades often are. The probability of any given data point, capital Z, being less than a certain value, lowercase c, is symbolized with the Greek letter phi, so we call this phi of z. Since normal distributions are shaped like a bell-shaped curve and are symmetric, the phi of negative z equals 1 minus the phi of z. So for example, the z-score of 0.07 is a negative z-score of 0.93. These z-scores can be found on distribution tables online. If x is normally distributed 0, 1, it is called a standard normal random variable, centered at 0, with variance and standard deviation equal to 1. You can easily find the probability of a data point being between a and b for standard norm variables by simply computing phi of b minus phi of A. For a normal random variable with mu not equal to 0, or sigma squared not equal to 1, i.e. not standard normal, we have to subtract mu from x and divide by sigma to sort of balance x out. So for x normally distributed mu, sigma squared, and two constants a and b, the probability of x being between a and b is phi of b minus mu over sigma minus phi of a minus mu over sigma. Phi of b minus mu over sigma is called the z-score of b, or the probability that x is less than b. The same goes for a. Additionally, the probability of x being less than or equal to b is the same as the probability of x being less than b for a normal random variable. If x1, x2, xn are n random variables that are independent and they have the same probability distribution, in other words, the variables are IID, independent and identically distributed, then for n large enough, n is greater than or equal to 30, we have the sum of all of them is approximately normal n mu n sigma squared. Since binomials are not truly continuous, we have to add 0.5 to b and subtract 0.5 from a to correct the point so they're more precisely on the curve, as seen on the graph. This is called the correction for continuity, used when approximating binomials as normal. You can see this correction in the formula and graph. If x is normal n sigma squared, then p of x less than b equals phi of b minus mu over sigma. If n is binomial np, then e of n equals np, and var n equals np times 1 minus p. Also, the following conditions, called the success-failure conditions, must be met for binomial np to be approximated as normal. Confidence intervals are symbolized by 1 minus alpha, where alpha is called the significance. If x bar minus mu divided by sigma over square root of n is normally distributed 0, 1, then the confidence interval of mu is as follows. Note that the critical value is the same as 1 minus alpha over 2 on the above graph, and that the critical value times sigma over the square root of n is called the margin of error. If n is greater than or equal to 30, we can use s instead of sigma. Also, when subtracting two sample means, they are normally distributed as follows, with standard deviation as shown. For normally distributed samples smaller than n equals 30, where sigma is unknown, you have to use a t-critical test instead of the z-critical test. In other words, finding phi using the t-distribution table instead of the normal table. We often deal with degrees of freedom in statistics, which accounts for the number of values that have the freedom to vary. For a single sample, for example, you typically say that the degrees of freedom is n minus 1. So for example, if you had 7 outfits and chose to wear one each day of the week, you would have the freedom to choose between options for the first 6 days. 7 shirts to choose from the first day, 6 for the second, and so forth. But you would only have one outfit left on the last day, which you would have to wear. So the degrees of freedom would be 7 minus 1, or 6. For 2 samples, you could use df as the smallest number between n1 minus 1 and n2 minus 1, or use the Satterthwaite formula. For pooled variance, where samples are small, df is n1 plus n2 minus 2. We can also measure the standard area, or the difference of the two sample means, using the following formulas. This is an estimate of the standard deviation of the difference between the means. When we test hypotheses, we must follow a certain procedure. First, we have to compute the test statistic, which is x minus mu divided by sigma over n. Then, we have to assume that h0, also called the null hypothesis, is true. The null is that mu equals mu naught, whereas HA, or the alternative hypothesis, is that mu does not equal mu naught. Finally, we compare the test statistic with the null. If it's inconsistent, we reject the null, and if it's consistent, we fail to reject the null. There are many ways to test for consistency. First, you could use R0, or the rejection region, for H0. If the test statistic belongs to the rejection region, you reject the null. If it does not belong, you fail to reject. Second, you could use the p-value. If the p-value is less than or equal to alpha, you reject the null, and if it's greater than alpha, you fail to reject the null. Note that failing to reject the null means that the mean belongs to the confidence interval, whereas rejecting the null means it doesn't belong. Also, for two-sided p-tests, use p-value over 2 and alpha over 2, and multiply by 2 at the end to get the p-value. If we drop the assumption that the sample n is much smaller than population n, we use the finite population correction. This involves multiplying sigma squared divided by n by the population n minus the sample n over population n minus 1. Note that some common z-critical values are as follows. When dealing with proportions, we again have certain success failure conditions, which are as follows. If the conditions are met, the sample proportion is normally distributed as follows, with sample error and z values as follows. An interesting concept that you may come across in problems is that the maximum value of y equals the square root of p times 1 minus b is achieved at p equals 1/2. When subtracting normally distributed sample proportions, the distribution, z-score, and standard error are as follows. When there is a small sample, we use the pooled standard error, shown below. There are many different types of statistical tests. The chi-squared goodness of fit test is used to find out how representative the sample data is of the real data. The degrees of freedom and formulas are as follows. The chi-squared independence test tests the independence of two variables. For both chi-square tests, you should use the chi-square distribution table. The F test compares variances between two normal populations. The formulas for the value of F and the critical value are as follows. Additionally, if you choose to use the statistical program R, you can use the corresponding R command shown. The final statistical test is analysis of variance, or ANOVA, which is used to compare the means of more than two populations. To find the value of F, you have to find the mean squared variation divided by the mean squared error, or MSG over MSE. The formulas and corresponding components are as follows. Note that the critical value is found by plugging in alpha, DFG, and DFE to the formula F alpha star, DFG, DFE, and then using the F distribution table. Also note that most tests can be one or two-sided, whereas ANOVA and chi-square tests are always one-sided. Finally, keep in mind that the best way to understand all of these statistical tests is to practice using them. Here is the key idea, or possibly the key idea, to remember. You are given parameters in probability. In other words, you somehow have access to the whole population. Whereas in statistics, you are not given parameters and instead make inferences. You can use this idea to quickly recognize a problem type. Thanks for watching, and I hope you found this crash course helpful.